everyone. My name is Francois, and today I'm going to be talking to you about fair unsupervised learning. First of all, a very quick disclaimer. So this is just these are just my views and do not represent anyone else's views. So let us start with unsupervised learning and the fact that it is at the heart of many machine learning applications, either as a standalone model or as part of a pipeline. Research on fairness in unsupervised learning has been carried out at the application level, so for PCA, k-means, or spectral clustering, for example. Defining fairness is not trivial in the case of unsupervised learning. And so what we're trying to do is propose a general framework that's going to encompass a lot of both those metrics and actually those specific applications. So the framework within which we're going to evolve is that of GLRMs, which are generalized low-ranked models, whose goal is to approximate a data matrix with a low-dimensional factors and a dot product. So the definition of a generalized low-rank model is frankly just a loss function on the reconstruction error plus some regularization terms. And so this framework actually covers many, if not all, of the usual algorithms such as PCA, robust PCA, k-means, and so on. So fairness in unsupervised learning has been defined in a variety of ways. And I think there are three main categories of metrics for fairness in unsupervised learning. The first one has to do with social fairness, and that means that the reconstruction error should be the same across all the different groups. So this can be achieved, for instance, by minimizing the worst group average cost. Balanced fairness, on the other hand, means that different groups should have the same distribution across clusters. And so that's really an idea of representation. Last, individual fairness, which is claiming that two similar inputs or data inputs should have similar outputs. So we're not going to spend too much time on those definitions, and we're going to focus on the first one, but the framework we propose is actually able to handle all of those cases, and the reader is referred to the paper. So now we introduce group functionals, and the point of a group functional is to regulate the trade-off between different average losses, and you can find its expression there. It's just a way of ensuring that we know how to handle the loss in group 1 versus the loss in group K, for example, and how we're going to ensure that we keep learning and improving losses, but how also we're going to manipulate trade-offs. So many group functionals have been proposed in the literature and are well known. So the first one, for instance, is a weighted average. The second one is just the max function. We also have LP norms. We also have penalized learning. And so all of those actually fit within that framework. And we also note that losses can be multivariate and can depend on the exact fairness definitions. In our case, we just use a very specific group functional, which we call the weighted log sum exponential. And so long story short, this is just a soft maximum, and it is used in many applications. It has very nice properties. In particular, it is convex. It also interpolates between the weighted average when alpha is equal to 0 and the max function when alpha is equal to infinity. So when we try to fit a fair GLRM, then we can actually reuse many of the generic algorithms that already exist, such as alternating minimization or biconvex gradient descent. So let us jump straight to the results. What we can see is that, as usual, here we're representing k-means on 3 different data sets. And so, as usual, when we increase the fairness requirement, then the average loss also increases. Now, let us move on to another topic, which is that of out-of-sample generalization. And so with the same data sets, but considering this time a PCA, but results hold for different applications, what we see is that by looking at a test set, we see that quite often choosing an intermediate value of alpha rather than alpha is equal to 0, alpha is equal to plus infinity can actually be beneficial. So that's the idea of partial debiasing as in supervised learning. So to conclude, we've proposed a very straightforward framework to handle fair low-rank models, and we've introduced the notion of group functional to handle trade-offs across different losses. And so further research is required to examine fairness definitions in unsupervised learning and benchmark them and study out-of-sample behavior. Thank you.